Thank you, Martin, and thank you to the organisers for allowing me to be involved in this wonderful conference. I represent a technical diving community, again with two hats, one as a training director for one of the main technical diving training educator agencies, and the other one as a consultant for manufacturers of closed-circuit equipment. Much as with Mark, I've basically taken Martin's bullet points and tried to answer the usage of technical diving with Rebreather, so we'll just work through those one by one. Why are Rebreather equipment useful and important to the technical diving community specifically? Now, technical divers tend to have one main aim, to explore either wrecks, caves, mines, marine life, get footage of that for their own needs, and bottom time is everything. Basically, time to be able to spend on the project, on the object of desire, as opposed to hanging in the blue doing the decompression. So the longer the bottom time can be safely, the better. And CCR is an excellent opportunity or piece of equipment for this purpose. At the same time, whilst extending the bottom time, the technical diver wishes to reduce the decompression time, but within safety limits so that the decompression is still safe and complete to lower the risk of DCI. Also, it's a big advantage to reduce logistics. As technical diving has developed from the mid-80s through the last 15, 20 years, what's being achieved has grown and grown and grown. There's things that are being done now, dives in the 300, 400 foot range that were once the realm of only a few explorers are now relatively routine. And there's a couple of reasons for that. Firstly, training has improved dramatically by the agencies. Secondly, the equipment has improved hugely. If I remember back to my beginnings as a technical diver in the early 90s, doing my first 200, 300 foot dives, pretty much every single dive, piece of your equipment or your team's equipment would fail. Regulators would free flow, bits would fall off of them, and various other problems would occur. There were kind of one advantage to that, which sounds like a strange thing to think of that as an advantage. The divers at that time were so used to dealing with problems, to having things go wrong and solving them, that they developed a very good stress response mentality. They were used to dealing with problems. One of the things to overcome with the modern usage is that now equipment is so much more reliable thanks to the manufacturers. Training is much improved by accident analysis to improve training methods. These problems and equipment failures become less and less common. But it doesn't mean they're never going to happen. So I always dive my rebreather with an attitude of today is the day it's going to fail, and always carry adequate amount of bailout. The advantage here, though, with logistics is that we can run a project with the correct amount of bailout and not use it, meaning it doesn't have to be reblended, refilled, etc. for the next day of diving. So multiple days of diving can be operated with a lower level of logistics. Now, no dive or dive application should ever be driven by cost. So we shouldn't make the decision as to whether we should or should not make a dive on the cost of the gas or the cost of the equipment. But it is a big factor. Some of the dives that we've heard about today, and you're well aware of from other communities throughout technical diving, like cave explorations, etc., with the costs of helium and other consumables are incredibly expensive. With Rebreather, we can drive that down whilst increasing the safety. So how and why are rebreathers utilised specifically within the technical diving community or environment? Well, firstly, our technical diving community environment comes from the recreational environment talked about by Mark. Basically, a recreational diver wishes to push their diving, extend it into a new realm, a little bit longer, a little bit deeper, often because there is more of interest to see in those areas because less people go there. One key area of this is wreck diving. To dive a wreck that's never been dived, to dive a wreck that hasn't had everything removed from it, been salvaged either commercially or by recreational divers taking home souvenirs, to dive something that's not so much damaged by the weather, the currents, the tides, the waves, etc. So as well as going to deeper wrecks, divers would like to penetrate inside of them, so an overhead environment. The advantage of the rebreather there is, again, you're not having bubbles, so as well as the silence that Evan was talking about, you're not knocking particles from the ceiling once inside the wreck, so visibility can be maintained for the exit. So they're a particularly good tool for that. Also, if you wanted to go inside of the wreck, basically what you're not doing is using gas so quickly. So you have time to think. You can move slower. You can deal with potential entanglement problems. You have time to deal with problems. So the aim would be to increase bottom time, exploration time, and simplify the logistics of a penetration dive, an overhead dive, or a deep dive on a wreck. The second one would be wall diving. There's a lot of phenomenal wall diving around the world, the Caymans being an example. With the open circuit diver, it would be more traditional to go to the planned depth, spend a short planned bottom time, and then immediately have to ascend pretty much vertically through the stages of decompression. With the rebreather, because of the optimized usage of consumables or the gases, you can go to depth and then slowly contour up the wall, looking at different pieces of marine life and features on the way up. So you can massively extend the amount of time where you're actually looking at what you went to see, the marine life on this wall environment, photographing it, videographing it, etc. It also means a very efficient, maximized decompression profile for that ascent. Another key environment where rebreathers have been used to great success within the technical community these days is mines, man-made overhead environments. These are very, very complex environments, and there is a true overhead. So to penetrate further and further, especially in deeper galleries, large amounts of equipment would be needed for a diver to swim to those areas using all the gas and return if using open circuit. To repeat that dive the next day to further exploration would require the whole lot to be replaced. The beauty of a rebreather here is bailout gas can be staged but not used, so a multi-day project can extend into the environment. Also, a lot of the flooded mines worldwide are in cold water environments. So the problems that we heard about earlier at the Pierce Resurgence of coping with extreme thermal conditions are added to with the diving in the mine environment, but dealt with by using a rebreather because we're breathing a warm gas and a hydrated gas. So it extends our exploration distance while again simplifying the logistics of being there. So some training undertaken specifically for the technical diving environment that falls outside standard rebreather training from the other communities. One thing quite unique about a lot of technical rebreather diving is we're in an open ocean or an open environment, and the ascent is made through what is sometimes called a free ascent. It's down to buoyancy control, stage decompression, without often a truly fixed reference. Certainly where I come from in the UK, ascending from wrecks in strong currents, you're drifting, you're coming up under a marker buoy and a reel, so buoyancy control is absolutely precision. In the scenario where things do go wrong, the bailout strategy then becomes complex as well, because the bailout strategy will involve switches between numerous open circuit gases to try to replicate the ascent of the rebreather had it still been working, and the discipline behind the buoyancy and skills to achieve this safely within a team is fairly high. So training needs to be intense and begin with concentrating on back to basics, the buoyancy, propulsion and trim to keep the diver able to make those free ascents. Method operation requirements needed by the technical diving community. The technical diver goes into his environment, whether it be mine or wall or wreck, for one purpose, to see those environments. It's their hobby at the end of the day. They're going there because they want to. They may want to video it or photograph it for their own uses. So they're going to be concentrating on what's there. For this reason, the best type of rebreather technology to enable the diver to pursue those goals is something that has a fairly simple human-computer interface. Ideally, something that you don't have to keep reaching down and picking up the displays to see what you're breathing or what you're doing. So most of the key manufacturers now, their rebreathers involve some type of head-up display, giving vital information like the PO2, effectively the rebreather equivalent of analysing what you're breathing, and constantly. So effectively, the life support display can be looked through to what you went there to enjoy and see. Low work of breathing is critical as well, because rather than certain other applications where you'd simply descend, work and come up, the technical diver generally has to swim quite often to get to where he wants to go. Now, of course, with the advent of DPVs and diver scooters, often they don't need to, but again, planning for failures, the scooter may fail. So the lower the work of breathing in a variety of positions to look at the type of positions the diver would find himself in as a recreational diver makes for safety. And again, much like the example on the presentation on the Pierce resurgence earlier, planning around the idea that, okay, this rebreather breathes really fine. I can scooter, I can swim, and the breathing feels great. But what will it feel like if suddenly there's an emergency? The breathing rate goes way up above what is planned. So plan for a worst case scenario. Think of it like the way that cars are tested. The manufacturer drives the car into a concrete wall at 60 miles an hour to see how the passenger compartment copes. You don't want to try to do that to test your car. Somebody else did it for you. So independent testing on rebreathers to show what they're capable of in a stress scenario is very important there. Multiple on-loop bailout options. So something is wrong with the rebreather. An alarm system to tell you something is wrong with the rebreather. The ability then, if needed, to bail out momentarily to assess, and then options to return back onto the loop to keep that gas and consumables efficiency for the return journey. And standardization within teams. If bailout gas is available, it's better to plug that bailout gas into the rebreather if the rebreather is not compromised. But if a team has 3 different types of hose to plug bailout gas into the rebreather, it will only work for one diver. And this standardization extends beyond just bailout hoses to all forms of the equipment being used to effect inter-team rescue and assistance. So parts of the technical diving community where our SOP could be suitable for all the rebreather communities, things where we can learn from each other. We have a concept in some technical rebreather training called the 3 Pries. Pre-assembly checks, pre-dive checks, and pre-breathe. And this really comes back to checklists that's been discussed a lot throughout today so far. A checklist can either be on screen of the rebreather itself, so built into the software. It can be a standalone sheet that is worked through. It can be a plastic sheet supplied by the agency. It really doesn't matter as long as a series of checks are followed to ensure that every part of that rebreather is functioning correctly and safe for that dive. The pre-assembly checks could include things like mushroom valve checks to ensure that nothing is blocking the mushroom valves, holding them open, and the loop is only travelling in one direction. In other words, the CO2 can't be rebreathed by a failed valve. Cylinder and canister contents checks, so analysing the gases in the onboard cylinders, analysing the gases in the bailout cylinders, labelling them, and taking appropriate steps to prevent misuse at the incorrect depth. And then canister or absorbent canister contents. Is it fresh? Has it been packed correctly as per the manufacturer's guidelines for that specific rebreather? If it was used previously, the day before or something like this, is the time that has been put onto that canister logged accurately? Has it been kept sealed overnight so there's no contaminants could have got to it? And if you're not sure, just ditch it. Fully assembled unit, after these pre-assembly checks, follow the on-screen checks, the checklist sheet or the plastic check sheet of the agency that you were trained through or the manufacturer's documentation for that rebreather. It's basically like pre-flight checks. There's a series of sequences to make sure everything on the rebreather will work. Some people use acronyms to help them remember the components, but try not to use memory. Use something that is there in front of you every time. And most importantly, the pre-breathe. A well-executed pre-breathe will effectively recheck the components of the pre-assembly and pre-dive again. We're breathing the rebreather for a minimum of 5 minutes with the nose blocked, either by pinching the nose, wearing a nose clip or wearing a mask, watching the PO2 display. Because now, as well as checking that the absorbent canister will remove CO2, we're also checking that the oxygen injection system or other gas injection system, depending on the type of rebreather, is functioning. It is adding the gas, it's maintaining the desired level, the electronics is working, everything together is working. To give you an example of the importance of a pre-breathe, a friend of mine was diving in France at a cave site, and the group started their pre-breathe sitting on the rocks and the grass outside of the cave entrance, away from the water's edge, just sat on the ground. During the pre-breathes, one of the divers passed out, fell forward, slumped onto the floor with the 32-kilo rebreather on his back. So the other divers immediately stopped their pre-breathes, went over, assisted him, took the rebreather off, rolled him over, revived him. He came round. And the reason he'd passed out was his canister was 30 kilometres away in the house. He was so excited about the dive, he'd rushed, he'd got to the site without a canister even in his rebreather. He'd gone down the checklist with the canister internal and not visible. He'd passed all the checks, he'd gone to pre-breathe with his nose blocked, and within 2 to 2.5 minutes of it, passed out. Now, that was a human error, that was a mistake. But if he hadn't have made the effort to do that 5-minute pre-breathe correctly with his nose blocked, where he would have passed out would have been a couple of 100 meters into the cave, and he would have drowned. So the pre-breathe rechecked everything he'd already done and saved his life. And this doesn't really have any bearing on the community. This is rebreathers across the board. Thank you very much.